Our first example is the linear programming. And we consider example here. We have two decision variable in a factory. And the decision is how many door to produce and how many window to produce. So this is called decision. And the second one, we have an objective function. We try to maximize our profit. We assume for the profit per door per batch, we have a $300 US dollars. And for the window, we have $500. So this is our objective function. And we have a functional constraint or structural constraint due to the factory. And for the first plant, the unit production time is 1 hour. So 1 times D less than 4 and 2 times W less than or equal to 12. This is our upper bound. Okay. And the next one, 3 times D plus 2 times W less than or equal to 18. So for the third plane, we call it product mix. That is, we produce different product on the same manufacturing plant. And also we have non-negative constraint. That is, D and W should be non-negative. And the programming, which means that a military operation. Okay, because the origin of operation research starts from the Second World War. So we have some assumption about linear programming. The first one is divisibility. That is, our decision variable could be its decimal point. So for some situation, our decision variable is integer. For example, a person or setup cost, setup or not. So it's integer. So in this case, it's called integer programming. And the second one is certainty. Okay, we assume our coefficient, our objective here are all certain. So there are two approaches. In undergraduate study, they use sensitivity analysis. That is, once you have optimality, you analyze the effect or impact of the uncertainty on the optimal solution, which sometimes it is not good enough. So there are more advanced techniques in graduate school, for example, robust optimization or stochastic programming to deal with uncertainty. And the third one is proportionality. This is proportional. That is, when we increase the production of our product, it will sold out in the market. But in the real world, there are competition or economics of scale, or we have a discount. When we produce too much, right, we'll discount so that the product will be sold out, which is nonlinear effect. Or learning curve. When you are working on the manufacturing process, the working speed of a factory member will get increased if it works longer. And the final one is additivity. That is, we could combine the revenue together. We can combine this one together. But there are some nonlinear effects. For example, there are complementary or competitive product. Buy one, get one free, for example. So in this case, it will become a nonlinear problem. So once you relax one assumption, it will become another problem. So the integer programming could be offered in one semester, also for nonlinear programming. So we define some terminology for this one. The first one is called feasible solution. That is, you need to satisfy the all constraint. Okay, so for this one, it's not feasible because we need this one less than or equal to 18, but this one is 12 plus 12 is 24, which is larger than 18. So this one is not feasible. That is, you cannot use this number for your production plant. So this is your feasible region. And the next one is called optimal solution. Depends on your objective function, try to maximize or minimize. So when you try to maximize, it's called largest value. When you find the largest one, it's called optimal solution. And there are many three possibilities. One is one optimal solution, and the second one is multiple. As we see in the previous example, right? Shortest path, we have three optimal paths. The final one is no, you cannot find the optimal solution because you put too strict constraint. For example, if this one is here, okay, so you in the real world you need in the homework assignment or in the textbook, we always have a feasible set, but in the real world your feasible set might be empty. So in this case, you need to go back and check which one is too strict. And we'll briefly introduce the algorithm. The idea is developed by Danzig in 1947. You start from the origin and you try to improve your objective function by going this direction. And you reach this point, right? Because this is your feasible solution. And you try to improve again here. So you reach a local optimal. But later we'll say that for linear programming, local optimal is global optimal. So when you try to go this direction, right, your objective function will decrease. So you won't go that direction, you just start there. And there are some history about this problem. This is economist. It won the Nobel Prize for input-output model. Okay, when Danzig presented a paper in a conference when he was young, and one audience asked that the world is nonlinear, he just said, stand there, don't know how to answer the question. But one prominent monument helped him answer the question. Okay, so you could look at this article to appreciate the development of idea. And later in 1984, Kamaka developed an algorithm, which is polynomial time. And according to Danzig, this is his contribution. Okay, develop linear programming and objective function, even though we treat it as obvious after we learn the course. But in 1947, it's not so obvious. Okay, I invent the simplex method.